Hi everyone, it's Miss Spivey. Today we're going to be learning about redox reactions. So I need you to open up to page 13 of your Unit 6 book. I am at school making this lecture, so you will probably hear a couple of lunch bells ringing. So if that happens, I'm sorry, but I can't help it. So far in Unit 6, we have learned about synthesis, combustion, decomposition reactions, single replacement, and double replacement. And remember, a neutralization reaction is a double replacement reaction. So far we have learned about these 5 types, and in every single one, you are given the reactants, and then you can predict the products, okay? Now, in order to recognize a redox reaction, what we're going to be learning about today, you actually have to do a little bit of work. So you cannot simply look at a reaction and tell if it's redox, okay? A lot of the reaction types we've already covered, like synthesis, decomp, single and double replacement, they are also considered redox reactions, okay? So what we're going to go through today and looking at in our unit book is how to know when a reaction is a redox reaction and what that means is taking place. So open up to page 13, and I'll start reading that top paragraph to you. We learned to classify chemical reactions to help predict the products that would occur. You learned about composition or synthesis reactions, decomposition, single replacement, double replacement, and combustion reactions. There is another classification method that involves determining whether electrons have been transferred from one chemical to another. Highlight that sentence. There is another classification method involving whether electrons have been transferred from one chemical to another. These reactions are called oxidation reduction reactions, or redox if you're talking chemist slang. Many of the reactions that we have studied and classified in another way are also redox reactions. So what we're going to do is learn how to classify redox reactions. When you leave Chem 1, you'll learn how to balance redox reactions. But as I've mentioned before, you are not just going to simply be given reactants and asked to predict the products for redox reactions. You have to do a little bit of work. So let's look at what we should be doing first. So the key point of redox reactions is being able to determine oxidation states. So flip over to page 14. On page 14, there's a go-to list of rules and things that we need to look at, okay? So the definition, an oxidation state, top of page 14, is the charge that an atom would have if all of the bonds were ionic. That means that some oxidation states are real, and sometimes they are just an accounting method that we have to keep track of electrons in a chemical reaction. So we have worked with oxidation numbers since Unit 2, when we talked about how metals and nonmetals lose electrons to become stable and have 8 valence electrons. We've used oxidation numbers when we're doing our crisscross method. Remember, we know how to look up and cancel out charges. So what we're going to do now, so like usually, if I were looking at potassium nitrate, you would tell me that potassium has a +1 oxidation number, and that nitrate, our polyatomic ion, has a -1 oxidation number. That is still true. Okay, that's not changing. When it comes to writing chemical formulas and using the crisscross method, that is still right. Now, what we're going to do today that's different is, instead of looking at nitrate as a group, we're going to find an oxidation number for potassium and nitrogen and oxygen. Okay? In order to do that, when we look at big reactions, we'll be able to see if electrons have moved from one atom to another. Okay? So the rules for determining oxidation states, I'm going to use all of this list eventually, but I want to start looking at number 3. So number 2, sorry. The oxidation state for a monatomic ion is equal to its charge. So if we have a group of atoms, all of the oxidation numbers add up to the charge. Okay? Number 3, the sum of oxidation states of all of the atoms in a compound must be 0. So that means that when we look at potassium nitrate, KNO3, all of the positive and negative charges within this compound cancel out and equal 0. Okay, that's our big key thing. Now, rule 4, 5, 6, 7 are all encompassed in this list here. So when you are trying to find the oxidation states of every single atom in a compound, these are the first things we're going to look for. Look for oxygen. It's going to have a -2 oxidation number. Look for hydrogen. It's going to have a +1 oxidation number. Look for metals that are in group 1. They'll have a +1 oxidation number. Metals in group 2 will have a +2 oxidation number. From that point, if you happen to look at an atom that has no oxidate, like none of those 4 things, then you just use chemical nomenclature. Undo your crisscrosses, take it one piece at a time. My big thing to help is to work from the outside in. That is particularly important when we're looking at compounds like KNO3 that I have 3 total atoms. So let me show you an example on KNO3. So if we're trying to find the oxidation states, oxygen is in my list. Its oxidation state is going to be -2. Now, I have 3 oxygens. So that means that overall oxygen is giving, so this is our scratch work that we're going to have down at the bottom to help us make sure that my compound is neutral. So -2 times 3 is a -6 charge. Okay? So that's not what we want. We want it to be neutral. So it's paired with potassium. Potassium's in group 1. So it's going to have a +1 oxidation number. +1 times 1 means that right now in my compound, -6 plus 1 is -5. Okay, so right now my compound with just potassium and just oxygen, there's a -5 charge. So that means because all compounds are neutral, that means that the nitrogen has to have an oxidation number of +5 within this compound. Okay, we know that if we're writing a chemical formula, nitrogen's oxidation number is a -3. That doesn't change. Nomenclature, everything you learned in Unit 5 has not changed. Okay, we're just looking, we're using this as an accounting method. So I have 1 potassium, +1 times 1 is +1, -2 times 3 is -6. That gives us a -5 charge. That's how I knew that nitrogen had to be a +5 charge this time within that compound. Okay, let's practice a couple more of those before we apply it to a chemical reaction. Okay, so let's look at potassium chlorate, KClO3. Remember, my list is I look for oxygen, then I look for hydrogen, a group 1 or a group 2. So I see oxygen. I know its oxidation state is a -2. So I'm going to do some scratch work down at the bottom to help me make sure that my charges cancel. -2 times 3 is -6. Okay. Potassium is in group 1. It has a +1 oxidation number. +1 times 1 is a +1 charge. So +1 plus a -6 gives us -5. So that means our oxidation state for chlorine is going to be a +5. Okay, so here are our oxidation numbers. Everything else down at the bottom is just scratch work. So it does not matter to us. It was just a method to help us be counting well. All right, let's look at the next one, KCl. Potassium's in group 1, so it has a +1 oxidation number. +1 times 1 gives us a +1 charge. And so that means that chlorine's oxidation number is going to be -1. So see, that one's easy. That's just like what we've been doing. It's the ones where we have more than 2 atoms that we have to really be careful about. Okay, so now let's look at carbon dioxide. All right, carbon dioxide, oxygen's in my list. So it's going to have a -2 oxidation number. -2 times 2 is -4. So that means that in order for my compound to be neutral, it needs to cancel out with a +4. So that's going to come from carbon. +4 times 1 is +4. So again, this is my answer. Whereas the bottom part is just scratch work to help me make sure that my compound is neutral and I'm following rule number 3. Okay, so SF6. I don't have oxygen or hydrogen. I don't have anything in group 1 or group 2. So I'm just going to use chemical nomenclature. I know that fluorine has a -1 oxidation number, okay? It's always -1. Remember, just like in nomenclature, start with that anion first. So -1 times 6 is going to give us a -6 charge. So that means that sulfur needs to give us a +6 to cancel out. So here would be our oxidation numbers. Okay. Now, I put nitrate down at the bottom because, again, you know that nitrate has a charge of -1. We've made you memorize that. But we need to find the oxidation state for nitrogen and oxygen. Okay, so oxygen is going to be -2 according to my list. -2 times 3 is -6. Now, this is not an ion. It's not a this is not a compound. It's an ion. So I need the charges to add up to a total -1 charge. So -6 plus 5 would give us a -1 charge. So we're doing lots of little easy mental math. Okay, we have to remember that our compounds are neutral. Compounds are neutral. Okay, we also have to remember that every atom now needs an oxidation state. So with redox reactions, every atom now needs an oxidation number. That's what I've been doing. That's what we've been covering here in the first couple minutes of the lecture. Okay, make sure all your oxidation states cancel out except for the off chance that you happen to have an ion that we're looking at. Now, we're going to take this skill and we're going to apply it to looking at reactions. Okay, so how to determine if a redox reaction is occurring? We're looking to see if electrons are gained or lost. Well, you and I both know that you can't see electrons. That's why we are looking specifically at oxidation states and if they change. So, in order for a redox reaction to take place, electrons are gained or lost, and we are looking at our oxidation states. So, what we were just doing with finding oxidation states for all of the atoms within a compound is what we're going to do now. So, this ALI3, we're going to follow our same system that we were just doing. I know that iodine has a -1 charge. -1 times 3 gives us a -3. So that proves that aluminum should be +3. Very good. So what about these free elements? What are we going to do with them? That's where I want you to look at page 14. So on page 14, rule number 1 says the oxidation state of a free element is 0. So these free elements, their oxidation state is a 0. Okay, so I know that I have a redox reaction because aluminum does not have the same oxidation number on both sides of my arrow. Neither does iodine. Okay, so this tells me that I do in fact have a redox reaction. So like I mentioned, we have to do a little bit of work, but then we can tell what has happened to our electrons. So let's see what we need to do now. When you have a redox reaction, that means that you have an oxidizing agent and a reducing agent. Okay, so when an atom is oxidized, that means it loses electrons. So think about cations. When cations lose electrons, they become positive. Become more positive. Okay? Reduction is gaining electrons. Think about anions. When you gain electrons, you become more negative. So let's look at the reaction that we just looked at. Aluminum went from 0 to a +3. So using my oil rig mnemonic device, I can see that because aluminum went from 0 to +3, it is oxidized. Okay, so that means that iodine, so 0 to -1, was reduced. Okay, and that might seem a little weird too, but it just really takes practice. So flip over to page 15 in your unit book. We're going to work a couple of examples together. So first thing we have to do is assign oxidation states. So I see sodium, it's a free element, its oxidation state is 0. I see chlorine, another free element, its oxidation state is 0. Now when I look at my compound, sodium's in group 1, it has a +1 oxidation number, so chlorine's going to be a -1 oxidation number. I know that this is a redox reaction because sodium's oxidation number changed and chlorine's oxidation number changed. So that means that somebody was oxidized and somebody was reduced. So sodium went from 0 to a +1, so it was oxidized because it lost electrons. And so chlorine went from 0 to -1, and so it was reduced because it gained electrons. Okay, let's look at another example. Let's look at number 2. All right, on this one, 2KClO3, I'm going to find my oxidation states here. So oxygen is -2 times 3 is -6. +1 times 1 is +1. So this right now, remember this is our scratch work. So that gives me a -5 charge. So chlorine needs to be +5. Potassium's +1 and -1. And then oxygen is a free element here, so it's 0. Okay? So when I look for things that change, chlorine changed. It went from +5 to a -1. And oxygen changed. It went from -2 to 0. So this is another redox reaction. So somebody was oxidized, oil rig. So oxidation is losing electrons and becoming more positive. So that was actually oxygen this time. It went from -2 to a 0. So it was oxidized because it lost electrons. So chlorine went from +5 to -1. It was reduced because it gained electrons. Okay. All right. On this last one, skip down to number 4. Pause the video. You all go through and assign oxidation numbers, and then we'll discuss whether or not it's an oxidation reaction or not. Okay. So hopefully after assigning oxidation numbers, this is what you got. When you're looking at silver, remember we learned in Unit 5, chemical nomenclature, that silver always has a +1 oxidation number. So as we're looking back and forth across our arrow, silver's oxidation number does not change. It's still the same. Nitrogen's oxidation number does not change. +5, +5. Oxygen does not change, and neither does potassium. So I have no change in oxidation states. So this is not a redox reaction. So if you don't have a redox reaction, then nothing is oxidized, nothing's reduced. You cannot apply oil rig. Cannot use oil rig. Okay, so what I want you to do is pause the video, and I would like for you to work number 3 and number 5 on page 15. Work it to the best of your ability, and then resume the video and check your answers. All right, so after pausing the video and working through your oxidation states, hopefully you got the same values I did. Remember, when you have a free element, it's 0. It's not within a compound. If it is within a compound, we're looking for our starting 4 atoms and then just using chemical nomenclature. Both of these are redox reactions, so I could apply oil rig. Oxidation is losing electrons, becoming positive. Reduction is gaining, becoming negative. So you can see who was oxidized and who was reduced. Now, some last things before I finish up and tell you how to get more practice. Notice that when I'm trying to find if something's oxidized or reduced, or trying to find their oxidation states, I'm ignoring the coefficients. Okay, I don't need the coefficients when I'm trying to determine oxidation states. Okay, and as you can see from this reaction, this is a synthesis reaction. Free element plus free element gives us a compound, but it's also classified as a redox reaction because I have those change in oxidation states. Okay, same thing for number 2. Number 2 is technically a decomposition reaction, but because we went through and looked at all of our oxidation states, we can see that electrons changed from one atom to another, giving us a redox reaction. So what you should do to practice redox reactions is go over to page 16. Page 16, and go ahead and do 6 through 10. But know that number 10 is challenging. Okay, that's as big as it's going to get. A-L-L-E-N, challenging. Sorry, I can't write and talk at the same time. Number 10 is challenging. It's going to be as hard as it gets here in Chem 1. So if you can do 6 through 9 all on your own, then you should be good to go. What I'll do is I'll put the answers to 6 through 9 on another slide. So pause the video, do them on your own, and then you can immediately check and see how you did. And if you have questions, feel free to see one of your chemistry teachers. Thank you for watching. All right, and last but not least, here are the answers to 6 through 10. In order to figure out if an atom was oxidized or reduced, you had to go through and assign oxidation states. So if you want a more detailed look at what the oxidation state should be, see a chemistry teacher, ask for help, and if you just need more practice with assigning oxidation states, a chemistry teacher would be happy to give you compounds to work on. So thanks for watching.